Swayam Prabha. Digital India. Educated India.
Good morning. So, in the previous module we looked at the Bartra model and we found out the Bartra-Nash equilibrium, and surprisingly we got the result that the price chosen by the firms is exactly equal to the marginal cost. So, this was identical to the outcome that we would expect in a perfectly competitive market, and with just two firms in the Bartra model, the outcome was that firms are choosing a price which is exactly equal to marginal cost. So, this is called the Bartra paradox, and thereafter we were interested in asking, well, this seems a little bit peculiar that with just two firms we are having an outcome which is exactly identical to what we would expect in a perfectly competitive model. So, how can we get out of this Bartra paradox? And to that extent we introduced an analytical framework of product differentiation, wherein we said that in the basic Bartra model, the two firms were producing homogeneous goods, identical products. The goods were perfect substitutes. But in the real world, when we look at products, the goods produced by two firms need not be perfect substitutes. So, when we added this element of product differentiation in the model, we got a result that the price chosen by the firms is strictly greater than the marginal cost, and we got out of the Bartra paradox. So, in today's module what we want to do is we want to present two other frameworks, one in which we are going to relax this assumption of capacity constraints, right. So, recall that in the Bartra model we said that if firm 1 were to undercut firm 2, then all consumers would go to firm 1 and firm 1 has enough capacity to serve the entire market. So, now we are going to relax that assumption, we are going to put constraints on the capacity because building capacity is expensive. So, we will say that firms do not have infinitely large capacity. So, and then we will ask, once the capacity constraint is introduced in the Bartra model, how does the outcome of that model change? So, we want to talk about capacity constraints. So, capacity constraint in the Bartra model. And the reason this is important is that there is a good reason why a firm's decision to charge a price higher than what its rival charges would not result in the complete loss of all its customers. So, this is because a firm, the rival, does not have the capacity to serve the entire market. The rival does not have the capacity to serve the entire market, right. So, let us frame this in the context of a particular example so that it will be easier for us to understand what is going on. So, let us say that there are two firms A and B, each of whom now have a capacity of let us say 1800 units, right. So, the capacity of each firm equals KB equal to 1800 units. In other words, the total capacity from both the firms combined is 3600. units, right. Let us suppose that the demand curve, that the market demand is given by the following equation. The market demand is QP equals 6000 minus 60p. So, the market demand is given as QP equal to 6000 minus 60p, and let us suppose that the marginal cost of firm A is equal to the marginal cost of firm B is equal to rupees 10 per unit, right. So, we are taking, so even in our previous analysis we took the marginal costs to be constant at C. Even now we have the same marginal cost, which is equal to rupees 10 per unit, right. And the question that we are asking is, in this setup, what is going to be the Nash equilibrium? What is the Nash equilibrium in this model, right? This is what we are interested in answering, right. Now before, so to get to the final answer, let us first ask, in the Bertrand model, firm 1 and firm 2 charging a price exactly equal to the marginal cost was a Nash equilibrium, right. The marginal cost here is rupees 10 per unit. So let us first ask, is P1 or rather PA PB equals 10 comma 10 a Nash equilibrium, right. Is PA PB equal to 10 a Nash equilibrium? Now, the quantity demanded at a price of 10 rupees per unit is based on the, so our demand curve is 6000 minus 60p. So, when the price is 10 rupees per unit, the total quantity demanded is 6000 minus 600, which is 5400. So, that is 5400, which is greater than the total capacity of the two firms, which essentially means that if firm A were to charge, let us say, a price of rupees 11 per unit, firm B will only find it profitable to undercut firm A's price and charge, let us say, 10.9, right. So, firm B will only find it profitable to undercut the price to, let us say, rupees 10.90 if it can serve all the customers, right, only then it makes sense, right. So, if firm B, if firm A were to charge rupees 11 per unit and I am firm B, so I would want to undercut firm A. So, let us say firm A's price is 11, so I want to bring it down to 10.9, and by bringing it down to 10.9 I want to capture the entire market demand. Let us see whether it is possible or not. Now, again let us go back to our market demand curve, it is 6000 minus 60p. So, at a price of 10.9, so the quantity demanded at P equal to 10.9 essentially is 6000 minus 60 times 10.9. So, this arithmetic gives us an output of about 5346, and firm B cannot meet this demand because its capacity is 1800 units, right. So, the essence that I can undercut my rival and capture the entire market demand no longer exists. So, thus 10 comma 10, the baseline Bertrand Nash equilibrium that we had in our Bertrand model is no longer a Nash equilibrium, right. So, B cannot meet its demand as its capacity is 1800, as its capacity equal to 1800, right. So, essentially what this means is, so with capacity constrained binding, a firm charging a higher price, than its rival, loses all its customers if its rival, right. So, with capacity constraint binding, a firm charging a higher price than its rival loses all its customers if its rival has enough capacity to serve them, right. So, I undercut my rival, all the consumers come to me and I have enough capacity to meet the entire market demand. If that happens, then the price being equal to marginal cost would be a Nash equilibrium, but if that is not true, which is not the case in our current setup, because by undercutting the rival I cannot meet the entire market demand, P1 equals P2 equals the marginal cost is no longer a Nash equilibrium, right. So, the Bertram model outcome of price being equal to the marginal cost is no longer a Nash equilibrium in our current model, which then leads us to the question as to what then is the Nash equilibrium. So, let us think about it. Okay. So, our demand curve here Q equals 6000 minus 60p, right, and the marginal cost, the capacity Ka plus Kb equals 3600 and the marginal cost equals 10. So, let us keep this in mind, right. Now, so let us think about what could be a possible candidate for a Nash equilibrium, right. Let us suppose that the entire capacity is being met of 3600 is being met, right. So, in other words, if all the 3600 units, which is equal to the combined capacity of the two firms, was met, what would be the price that would be obtained? So, this is 2400 divided by 60. So, that would lead to a price of rupees 40 per unit. So, right now we are going to make the following claim and we are going to prove it, right. So, 40 comma 40 is a candidate for a Nash equilibrium. 40 comma 40 is a candidate for the Nash equilibrium and we will verify, and in particular this is the price at which the total quantity demanded is exactly equal to the capacity, of 1800 units, right. So, now, to verify whether 40 comma 40 is a Nash equilibrium, what we need to do is, so suppose firm A charges 40, can firm B do better than simply charging 40, right. So, if we wanted to show that 40 comma 40 is not a Nash equilibrium, then all we have to show is that if firm A charges 40, firm B has a strictly profitable deviation, right. So, suppose firm A is charging PA equals 40, right. So, suppose firm A is charging a price of 40, right. Does firm B have a strictly profitable deviation? If yes, then 40 comma 40 would not be a Nash equilibrium. Right. So, let us ask. So, what do I mean? What do we mean by firm B having a strictly profitable deviation? Either it can charge a price larger than 40 or it can charge a price smaller than 40, right. So, firm B has no incentive. So, B has no incentive to lower the price below 40. The reason being, it can sell as many units as it wants at a price of 40, right. So, if by lowering the price and I was able to sell more, perhaps B might benefit, but currently, regardless of what A is doing, and currently A is charging a price of 40 and it can't meet the entire demand. So, firm B can sell whatever it wants to sell up to its capacity at a price of 40. So, B has no incentive to lower the price below 40, as it can sell what it wants to sell at 40, right. What now does firm B have an incentive to raise price? So, let us ask, does B have an incentive to raise its price? Let us check about this, right. And to answer this, let us ask, what is firm B's residual demand? So, firm B's residual demand, so let us call it as dr. Firm A has a capacity of 1800. So, let us say firm A has met its capacity, has sold 1800 units. So, firm B's residual demand essentially is 6000 minus 60p minus the 1800 units, which essentially means dr is 4200 minus 60p. Let us rewrite this in the form of an inverse demand curve, right. So, let us rewrite this as, or rather let me call this as QR, right, let me call this as QR, right. So, we will write this as P equals 70 minus 1 upon 60 Q. So, this would be the residual demand curve for firm B, which then would mean that the residual marginal revenue curve. So, the inverse demand curve is linear, the marginal revenue curve will have the same intercept, but will be twice as steep, 1 minus 30 times Q. So, when I set the marginal revenue to equal my marginal cost, essentially I am setting 70 minus 1 upon 30 Q. Why would I do that? I want to figure out what is the optimal quantity, right. So, essentially I behave like a monopolist with respect to the residual demand. The residual demand is 70 minus 1 upon 60 times Q. So, I choose what is the optimal quantity that I want to sell based on this residual demand curve, right. So, I essentially behave like a monopolist with respect to this residual demand curve. So, that is equal to 10, the marginal cost. Notice this gives me an output of Q star, which is exactly equal to 1800, which is exactly equal to my capacity, right. So, and if I were to if I wanted to sell these 1800 units, if I wanted to sell those 1800 units, the price that I would charge is 70 minus 1 upon 60 times 1800, which would give me a price of 40. So, if firm A charges 40 rupees per unit, firm B has no incentive to lower price and also has no incentive to charge a higher price. So, firm B charging 40 is the best response to firm A charging 40. So, B charging 40 is a best response to firm A charging 40 rupees per unit. And we can have a similar argument wherein we can show that if firm B were to charge 40, does A have any strictly profitable deviation, which means does A have any incentive to lower or increase its price above 40, and a similar argument will tell us that if A charging 40 is also a best response to firm B charging 40, right. These two statements would then imply that 40 comma 40 is in Nash equilibrium, right, right. And notice that prices are immediately greater than the marginal cost. So, we no longer have the Bertrand paradox. The only thing that we want to check is 1800 units the right capacity for the two firms, right. So, because the capacity was 1800, we figured out that if firms are meeting that entire capacity, the price will turn out to be 40, and that turned out to be the Nash equilibrium. But what we want to ask is 1800 indeed the right capacity for the firms, which means do the firms have any incentive to use a capacity which is or set up a capacity which is smaller than 1800 or larger than 1800. So, let us ask whether firms have an incentive to either lower the capacity or increase the capacity, right. So, suppose firm A had chosen a capacity of 1700 units, right, while B has chosen a capacity of 1800 units, right. So we want to check whether 1800 is the optimal capacity or not. So we are asking, well, suppose, right. So A has chosen a capacity of 1700 units. Now if these are the capacities of the two firms, then 40 cannot be the equilibrium price, because 40 was the equilibrium price when the total capacity was 3600, which is 1800 plus 1800. Now the total capacity is 3500. So 40 cannot be the equilibrium price. 40 cannot be the equilibrium price now. As the total quantity demanded, of 3600 is greater than the current capacity. Right. So then what is the new equilibrium price? So then let us first figure out what is the residual demand curve for A, what is the optimal price that it would choose, what is the residual demand for B, what is the optimal price that it would choose, right. So let us look at firm A first. So firm A's residual demand is 6000 minus 60p minus the 1800 that firm B is selling. So this essentially means QR is 4200 minus 60p as we had earlier. Right. So we can rewrite this in the form of an inverse demand curve. So PR is 70 minus 1 upon 60Q, exactly what we had earlier. So the marginal revenue is 70 minus 1 upon 30Q. Right. So let's graph this again. So Q quantity price. So at Q equal to 0, I have a price of 70. This is what it looks like. I have a marginal cost of 10 here. This is the marginal cost, and this is the capacity of 1700. So the 1700 capacity is here, right. So if this is the capacity constraint, now notice at Q equal to 1700, the marginal revenue is 70 minus 1 upon 30 of 1700. So the marginal revenue at Q of 1700 is essentially 70 minus 1700 by 30. So that is 210 minus 170. So that is 40 by 3, which is greater than 10. So my marginal revenue curve, so if I wanted to draw the marginal revenue curve, so that marginal revenue curve essentially would be something like this. So this would be 13.33, right. So whatever 40 by 3, whatever that number would be. So essentially the marginal revenue is greater than the marginal cost at its capacity point, right. Similarly, if we were to do it for firm B, right, so what would be firm B's residual demand? Firm B's residual demand would be 6000 minus 60p minus the units that firm A sells, which is 1700 units, which essentially means QR is 4300 minus 60p. So we can rewrite this as an inverse demand curve. So 4300 divided by 60, so that would give us 71.67 minus 1 upon 60 Q, which would imply that the marginal revenue for the residual demand curve for firm B is 71.67 minus 1 upon 30 Q. If you were to draw this for firm B, we would get the following. So at Q equal to 0, the willingness to pay is 71.67, and this is what it would look like. I have a marginal cost of 10 here, and we have the capacity of firm B, which is 1800. So if we were to draw the residual marginal revenue curve, now notice this is 71.67 at Q equal to 1300, this term would be 60. So 71.67 minus 60 would be 11.67. So essentially now the marginal revenue curve, this would be about 11.67, right. So the marginal revenue is greater than the marginal cost, for both the firms, right. So the optimal price, So that essentially means that both firms are operating at their full capacity. So firm A is operating at its capacity of 1700 units, firm B is operating at its capacity of 1800 units. These are the optimal choices of Q chosen by the firms. So the optimal price, is obtained by setting the total capacity, which is 3500, to equal 6000 minus 60p, which gives us the price as 41.67, right. So 41.67 charged by the firms is a Nash equilibrium, right. So at A's capacity of 1700 and B's capacity of 1800, this is the optimal price which is charged. But note that, right. So however, this Nash equilibrium is not as profitable, right. This Nash equilibrium is not as profitable for A. This Nash equilibrium is not as profitable for A as setting 1800 capacity, right, because now the profit for firm A with a capacity of 1700. So the price that it charges is 41.67 minus the marginal cost of 10, and it sells 1700 units. This is approximately 53,839. But if it were to stay with its capacity of 1800 units, and recall, when the capacity is 1800 units for both the firms, the Nash equilibrium price which we showed earlier was equal to 40. So that is 40 minus 10 times 1800, so that is 54,000, right. So clearly choosing a capacity of 1800 is better than choosing a capacity of 1700. So choosing a capacity of 1800 is strictly better than choosing a capacity of 1700 for firm A, right. So we started with the case that suppose A had chosen a capacity of 1700 units while B had chosen a capacity of 1800 units, and we found that clearly A choosing 1700 is less optimal than choosing 1800. Okay. Now we want to check the second case, which is so suppose A chooses a capacity. Suppose A chooses capacity of 1900 units and B has a capacity of 1800 units as before. And B has a capacity of 1800 units. Okay. So what is the Nash equilibrium going to be, and how does this play out? Okay. Now we can infer that if A chooses a capacity of 1900 units and B has a capacity of 1800 units, then at least one firm has to lower its price to below 40 to clear the market, right. Firm B has no intention for a price cut. Has no incentive to cut its price. Why is that so? Because if it keeps 40, it will serve its entire capacity of 1800 regardless of firm A's price, right. So because if it keeps the price at 40, it will serve its capacity of 1800 units regardless of firm A's price, right. So firm B has no incentive to cut its price regardless of firm A's price, because A can only serve 1900 customers, right. So, A can only serve 1900 customers. So, firm B has no incentive to lower its price to less than 40. Right. Now, let us look at what would be A's residual demand, right. So, firm A's residual demand is QR equals 6000 minus 60p minus 1800, which is as before QR equals 4200 minus 60p. So, as before firm A's residual demand is 4200 minus 60p. Now, the inverse of the residual demand PR equals 70 minus 1 upon 60 QR. PR equals 70 minus 1 upon 60 QR, which leads to a residual marginal revenue curve of 70 minus 1 upon 30 Q, right. At Q equal to 1900. So, let us see what is the marginal revenue at 1900 units. So, that is equal to 70 minus 1 upon 30 times 1900. So, that is 210 minus 190. So, that is 20 divided by 3, which is less than the marginal cost of 10, right. So, what happens is, so when A has a capacity of 1900 units, when it decides to choose the optimal quantity that it wants to produce, it turns out that at 1900 the marginal revenue is less than the marginal cost. So, marginal revenue essentially is less than the marginal cost, which is not a condition for profit maximization for firm A. So, this essentially means that if A has capacity of 1900, right, it does not want to use it. But building excess capacity is costly, right. But building excess capacity is costly. So, having 1900 units is not optimal. So, I would not want to use it. So, then why build that excess capacity at all in the first place? So, there is no point in building that excess capacity. So, which then implies that firm A has no incentive to bring its capacity down to 1700 units. It also has no rather A has no incentive to bring its capacity to 1700 units. It has no incentive to increase its capacity to 1900 units. So, each firm building capacity of 1800 units and charging a price of 40 is indeed a Nash equilibrium. Right. Another interesting finding here is the following, right. So, the other interesting finding is that this outcome is identical to what we would get in a Cournot model when there is no capacity constraint and the marginal cost is 10, right. So, this outcome is identical to what we would get in the Cournot model when there is no capacity constraint and the marginal cost is 10. So, let us think about this. So, the demand curve is 6000 minus 60p, right. So, the demand curve that we started with was Q equal to 6000 minus 60p, and so let us rewrite this as P equals, so if we rewrite this as 6000 divided by 60, so we will have it as 6000 divided by 60 minus 1 upon 60 p, right. So, essentially this would be 100 minus 60 p. So, or rather 60 q, right. So, 100 minus 60 q. Now, where this is of the form, so in our standard Cournot model we had an inverse demand function where p was equal to a minus b q. So, what was the Cournot output of each of the firms? The Cournot output q1 star, which is equal to q2 star, was essentially a minus c divided by 3b. So, what is the a? The a is 100, the marginal cost is 10, 3 times b. So, b is essentially 1 upon 60. So, essentially we have 90 and here we have 1 upon 20. So, this is equal to 1800 units, right. So, and notice 1800 was the capacity constraint that we have put in the Bartra model, and the Cournot price was a plus c divide a plus. So, the Cournot price would then be, so if this is 1800 units for each of the firms, so that would be 3600. So, so we would have the Cournot price a plus 2c divided by 3. So, that is going to be 100 plus 2 times the marginal cost, which is 10, divided by 3. So, that would be 120 divided by 3, which is equal to 40, which is the Nash equilibrium in the Bartra model. So, essentially the Bartra price competition with capacity constraints yields Cournot outcome. So, the Bartra price competition with capacity constraint yields the Cournot outcome. Okay. So, this is an interesting findings, right. So, one of the main takeaways is that the moment we relax the assumption of the Bartra model that the firms are constrained by capacity, are constrained by capacity, we no longer have a finding that the price is equal to marginal cost. In fact, we have prices which are strictly greater than marginal cost. And another interesting observation is that the outcome that we get in this model is exactly identical to what we would have gotten in the Cournot model, where the marginal cost was equal to 10 rupees per unit. Okay. Now, so let us look at one other extension of the product differentiation model. So, we saw the product differentiation model in the last module, right, and we learned that prices are going to be greater than the marginal cost. We want to look at a slightly different variant of that product differentiation model. We want to pitch it in the context of an horizontal product differentiation model, wherein we want to talk about spatial competition, right. So, we want to talk about spatial competition, right. This is due to Hotelling. So, this is also called the Hotelling linear city model. The Hotelling linear city model, right. So, our objective is to revisit the model of product differentiation, in the context of Hotelling's linear city model. Right. So, consider a line of unit length, right. So, consider a line of unit length. So, consider a line of unit length and consumers are uniformly distributed on this line. Consumers are uniformly distributed on this line, right. So, this market is served by two stores, by two firms or two stores, right, firms 1 and 2, right, and one of them is located at one extreme, the other one is located at the other extreme. So, one of them is located on the left hand side of the line, one of them is located at, let us say, x equal to 0. So, let us call this as firm 1 and the other is located at the other extreme of this line at x equal to 1. So, let us call this to be firm 2 being located here. So, each firm has a marginal cost of C, right. So, firm 1's marginal cost and firm 2's marginal cost are taken to be identical, as has been the case in all our previous models, and it is equal to C. Now, suppose that there are n consumers in total. And these consumers are uniformly distributed on this line. So, we define the consumer's location in the market. So, we define the consumer's location in this market. So, let us say we have some consumer who is, let us say x, we denote a consumer who is x. So, define the consumer's location in this market, right, as the consumer's most preferred product, consumer's most preferred product, right. So, if I am some consumer who is at the point x, then x is likely my most preferred product, but the two firms are located at the either end of the town. So, there is some disutility that I as the consumer get when I move to the location x equal to 0 to buy firm 1's product, or when I move to the location x equal to 1 to buy firm 2's product. Okay. So, we define the consumer's location as the consumer's most preferred product. Now, more generally we could interpret the x, right. So, consumer x who is located at a distance of x units from the left hand side of the market, right. It could also mean, right. So, we could interpret the x in the context of in the characteristics of product differentiation. So, what I mean by the following is x could be treated as the amount of sugar in a cereal, right. So, x equal to 0 would mean a cereal with no sugar content, x equal to 1 could mean a cereal with 1 teaspoon of sugar added, right. So, even though we are measuring the geographical distance here, we are using the context of geographical distance to talk about product differentiation, in the sense that x, right, x could denote the number of teaspoons of sugar in a cereal, let us say, or it could even imply the amount of sugar in a soft drink, right. So, these could have various interpretations. Now, we will also assume that the consumer has a valuation of V for the product, right. So, his willingness to pay is V rupees for the product. Now, if the consumer purchases a product, so which means if I am someone who likes, let us say, half a teaspoon of sugar in the cereal, and I end up purchasing a cereal with absolutely no sugar content, or I end up purchasing a cereal with 1 teaspoon of sugar, then I incur some disutility, right, because I am not getting my most preferred product. If the consumer purchases a product that is not his ideal product, the consumer incurs a utility loss, right. So, consumer incurs a utility loss, right. So, specifically the consumer incurs a cost. So, incurs a cost of T times x if good 1 located at x equal to 0 is consumed, and incurs a cost of t times 1 minus x if good 2 located at x equal to 1 is consumed, right. We could, so the fact that I am consuming a product which is not my most preferred product leads to a disutility, right, and the cost is t times x if good 1 is consumed, t times 1 minus x if good 2 is consumed. Okay. Now, so let us again sort of capture the line here. So, 0 1 and let us say I have some consumer, let us call this xm, right. So, for this x mth consumer, so let us take this consumer, if the consumer buys good 1 at price P1, so the consumer buys good 1 at price P1, then the consumer surplus is going to be, well, his willingness to pay is V, right, the consumer is at xm, the consumer's willingness to pay is V, but because I bought, so this is good 1, firm 1 which is selling good 1 here and firm 2 which is selling good 2 here. So, because I purchased a product which is not my most preferred product, my most preferred product is at xm, but that good is not available. So, I go and buy good 1 and I incur a disutility cost of t times, let us say xm, right. So, let us first write it as I pay a price P1, right. So, I pay a price P1. So, my willingness to pay is V, I pay a price P1 and then I also incur a disutility cost which is t times xm, right. So, this is my net gain or the consumer surplus if I buy good 1 at price P1. Similarly, the consumer surplus, the consumer buys good 2 at P2, the consumer surplus is going to be, well, my willingness to pay is going to be V. So, that is going to be my willingness to pay. I actually pay the price P2 because that is the price of good 2, but because I am buying it from firm 1 and this is not my most preferred product, I incur a disutility cost. So, that disutility cost is t times 1 minus x to the power m, right, or 1 minus xm rather, right, 1 minus xm. And let us suppose that this xm customer is the indifferent customer, right. So, there are consumers who are uniformly distributed. Let us say that this is the consumer who is indifferent between buying the good from firm 1 or buying the good from firm 2. So, suppose xm is indifferent between buying the good from firm 1 or firm 2, right. So, in other words, I am indifferent between buying it from firm 1 or firm 2, then that essentially means that the consumer surplus that I get by buying good 1 is exactly equal to the consumer surplus that I would get by buying good 2. So, that would mean that V minus P1 minus t times xm equals V minus P2 minus t times 1 minus xm, right. So, the V gets cancelled from both sides. So, I have P1 plus t times xm equals P2 plus t minus t times xm, which gives me 2 times t times xm is P2 minus P1 plus t, which then implies that xm equals P2 minus P1 plus t divided by 2t. So, this is what we would get. Similarly, 1 minus xm, right, 1 minus xm. So, 1 minus xm would be 1 minus this entire expression. So, that would be P1 minus P2, P1 minus P2 plus t divided by 2t, that would be 1 minus xm. The reason why we care about xm and 1 minus xm is because xm now is the fraction of consumers. Recall there are n consumers in total, xm is the fraction of consumers who buy the good from firm 1. Xm is the fraction of consumers that buy the good from firm 1, and 1 minus Xm is the fraction of consumers who buy the good from firm 2. Once we have the fraction of consumers who buy the good from firm 1 and firm 2, essentially we have figured out the demand for good 1 and the demand for good 2. So, the demand for good 1 essentially is Xm, and there are n of those consumers. So, that is going to be P2 minus P1 plus T divided by 2T times n, and the demand for good 2 D2 P1 P2 equals 1 minus Xm, which is P1 minus P2 plus T divided by 2T times n. So, we have the demand for good 1 and the demand for good 2. Notice that as expected, the demand for good 1 is decreasing as P1 increases, and it increases as P2 increases. Okay. So, each firm's demand is decreasing in its own price and increasing in the price of the other firm. Okay. So, with these demand curves, once we have the demand curves, we need to figure out what are the optimal prices which are going to be charged by the firms. So, in other words, we need to figure out what are the best, so to figure out what the Nash equilibrium prices are, we need to compute the best response for firm 1 for each possible choice of firm 2. We need to ask what is firm 2's best response for each possible choice of price of firm 1 and find out where the best response curves intersect. So, to do that, let us write down the profit function of firm 1. Profit function of firm 1 is P1 times D1 minus the total cost, the total revenue minus total cost. So, that is P1 minus C times D1 of P1 P2, which essentially is P1 minus C times. So, if I go back, I know that the D1 is P2 minus P1 plus T divided by 2T times n. So, that is P2 minus P1 plus T divided by 2T times n. Similarly, the profit of firm 2 is the price minus marginal cost times the demand, which is P2 minus C times P1 minus P2 plus T divided by 2T times n. So, we have the profits of the two firms. So, to find out the optimal prices, right. So, firm 1 believes that firm 2 will keep its price as P2. So, if I have, so I take the derivative of the profit function of firm 1 with respect to P1. So, we have n divided by 2T outside. So, we have P2 minus P1 plus T times the derivative of P1 minus C, which is going to give us 1, plus a P1 minus C times a minus 1, and this is necessarily equal to 0, right, which implies that P2 minus P1 plus T minus P1 plus C equals 0, which then implies that P1 as a function of P2. So, I am going to get 2 times P1, that is equal to P2 plus T plus C divided by 2. This is the best response of firm 1 for each choice of firm 2's price. Now, notice that since this is a game of price competition, the best response function for firm 1 is upward sloping, as opposed to the Cournot model where the best response function for firm 1 was actually downward sloping, right. So, this is a nature of this is a characteristic of the nature of the game. So, prices are strategic complements, quantities are strategic substitutes, right. So, now we have d pi 2 dp2, d pi 2 dp2 is equal to n upon 2t, n upon 2t. So, we have P1 minus P2 plus T. If I want to find out what is firm 2's best response, so plus P2 minus C times minus 1 equal to 0. This gives me P2, this gives me P1 minus P2 plus T minus P2 plus C equal to 0. So, the best response function for firm 2 is P2 of P1 equals P1 plus T plus C divided by 2. So, I have the two best response functions which are upward sloping. Now, if we were to plot these two best response functions, so this is P1 and this is P2. So, this is the 45-degree line. So, if I write down the best response function for firm 1 at P2 equal to 0, P1 is T plus C divided by 2. So, when P2 is 0, P1 is T plus C divided by 2, and then this is upward sloping, right. So, this is firm 1's best response function, and if I look at firm 2's best response function at P1 equal to 0, it is again C plus T by 2, it is T plus C, it is T plus C by 2 when P1 is 0, and firm 2's best response function is this. Well, the Nash equilibrium price P1 star P2 star are the set of prices which are mutually best responses. So, this is the Nash equilibrium price. So, essentially I have P1 star which is the best response to firm 2's choice of P2 star, and I have P2 star which is a best response of firm 1's choice of P1 star. So, if we solve these two simultaneously, so essentially I have from the first expression 2 times P1 star which is equal to P2 star, which is again P1 star plus T plus C divided by 2 plus, so I take the 2 here. So, 2 times P1 star equals P2 star, for which we substituted here, plus T plus C, and we were to simplify, we would get 4 P1 star equals P1 star plus 2 times T plus C plus T plus C. So, that is 3 times T plus C, which would give us P1 star equals 3 times T plus C divided by 3, which is T plus C. Similarly, we would have P2 star with, due to symmetry, P2 star also is T plus C, right. Now, this is the Nash equilibrium price that we have solved for. At these prices, the firms essentially split the market, right. So, if I go back and ask what is XM, so since P2 star and P1 star are identical, XM is essentially T divided by 2T, which is 1/2. So, 1 minus XM also is 1/2. So, the two firms, so XM equals 1 minus XM equals 1/2. So, essentially the firms split the market, and more importantly, the price charged by firm 1 is greater than the marginal cost, the price charged by firm 2 is greater than the marginal cost. Now, the role of T is actually quite interesting. If T were to tend to 0, essentially the price would boil down to the marginal cost, which is what we would get in the Bartra model. But T equal to 0 essentially would mean that there is no product differentiation, the goods are homogeneous. So, we would essentially replicate the Bartra outcome of price being equal to marginal cost. So, here is another setup where in the linear city model we have goods which are differentiated, and this differentiation leads to firms softening price competition by charging a price which is greater than the marginal cost. Thank you.